Tonight, we're going to answer a question that sounds simple but turns out to be one of the most technically difficult problems in astronomy and one whose answer carries more implications than most people realize. Where do we actually live in the Milky Way? Not in the poetic sense of somewhere in the galaxy, somewhere among the stars, but in the precise, cartographic, physically specific sense. What is the exact address of the solar system within the structure of the galaxy? How was that address determined? How confident are we in the answer? And what does the address reveal about why Earth is the kind of place it is? The difficulty of answering this question is worth emphasizing before anything else. Astronomers have been trying to map the Milky Way accurately for centuries, and the picture has changed dramatically multiple times, with each generation confident that its picture was correct until new data revealed it was wrong in important ways. The challenge is always the same. We are inside the object being mapped, embedded within the galactic disk, unable to step outside and take a photograph of the whole thing. Every map of the Milky Way we have ever made is an inference, a reconstruction from indirect evidence gathered from a specific location inside the system rather than a direct observation of the system from without. What we now know, assembled from radio observations, infrared surveys, parallax measurements, stellar spectroscopy, and the extraordinary dataset provided by the Gaia space mission, is that the solar system is located at a distance of approximately 26,000 light-years from the galactic center. It orbits within the disk of the galaxy in a feature called the Orion Arm or Orion Spur, a smaller spiral structure that connects two of the Milky Way's four major spiral arms. The solar system sits in a region of unusually low density called the local bubble, a cavity evacuated by ancient supernova explosions, at an elevation slightly above the midplane of the galactic disk. We are traveling at approximately 220 kilometers per second around the galactic center, completing one full orbit every 225 to 250 million years. Each of these facts is more interesting than it first appears. The distance to the galactic center, seemingly just a measurement, was the subject of a century of debate and was wrong by a factor of nearly 10 in early estimates. The Orion Arm, which sounds like a defined structure with clear boundaries, is actually a minor feature whose classification and extent are still debated. The local bubble, the cavity we inhabit, is an unusual environment whose properties have direct consequences for the heliosphere and therefore for life on Earth. The galactic orbit, the 225 million-year journey around the center, carries the solar system through different galactic environments, each with different properties, and this transit may have influenced Earth's biological history. By the end of tonight, you will have a complete, honest, and physically grounded picture of where in the galaxy we actually live, how we know it, what the environment around us is, and why our specific location appears to have been important for the development of the kind of planet and the kind of life that we represent. If this kind of complete, precise answer to a fundamental question about our place in the universe is what you come here for, subscribe and leave a like. It helps this channel reach people who want the complete picture rather than the oversimplified one. Now, let us begin with why mapping our own galaxy is so hard. The question also carries within it an implicit critique of how galaxy education typically works. Most treatments of the Milky Way in popular astronomy focus on the properties of the galaxy as a whole, its diameter, its mass, its age, its number of stars, without ever precisely pinning down the solar system's position within it. This is partly because establishing that position required a long scientific journey, and explaining it requires more than a single fact. The position of the solar system in the galaxy is not a single number but a combination of several independent measurements, each addressing a different aspect of location. Radial distance from center, angular position within the disk, elevation above or below the midplane, location relative to the spiral arm structure, and the properties of the immediate local environment. What makes this question particularly interesting is not just the answer but the journey to the answer, and the revelation at each step of how much larger and more complex the galaxy is than the step before suggested. Galileo's telescope resolution of the Milky Way into stars expanded the universe from thousands of stars to uncountably many. The discovery that the Sun is far from the galactic center expanded our understanding from a sun-centered galaxy to a vast system in which we are peripheral. The discovery of dark matter revealed that even the stellar galaxy is a minority fraction of the full galactic system. Each expansion has moved us further from the center of things, further from the natural human assumption that we occupy a privileged position. The core problem of Milky Way cartography has no precise analog in any other field of human endeavor. It is something like trying to draw an accurate map of a city when you are blindfolded, confined to a single room within the city, and can only infer the city's layout from the sounds of traffic, the patterns of birds flying overhead, and the occasional radio transmission from other parts of the city. You have access to real information, but that information is indirect, filtered through your specific location, and subject to interpretation in light of theories about how cities are typically structured. The specific obstacles that make mapping the Milky Way from inside it so difficult are several and distinct. The first is obscuration. The galactic disk, where we and most of the galaxy's stars reside, contains enormous amounts of interstellar dust that absorbs and scatters visible light. Looking from the solar system toward the galactic center, a sightline that passes through roughly 26,000 light-years of the disk, the extinction at visible wavelengths is roughly 30 magnitudes, which corresponds to a factor of about 1 trillion in brightness reduction. Stars that would be visible to the naked eye if there were no dust are completely invisible with any optical telescope, not because they are too faint but because the dust between us and them has absorbed essentially every photon they would have sent our way. This is not merely inconvenient. It means that the densest and structurally most important parts of the galaxy, the galactic center and the inner bar, are essentially invisible to optical astronomy. Understanding these regions requires radio observations, which pass through dust essentially unimpeded, infrared observations which are far less affected by dust than visible light, and X-ray and gamma-ray observations, which reveal the high-energy processes occurring near the galactic center. The second obstacle is depth perception. Even where dust is not a problem, determining whether two stars are actually neighbors or merely appear close together because one is much more distant than the other requires knowing the distances to both. For distant stars, determining distances is a major undertaking. Parallax, the most direct and reliable distance measurement technique, works only out to a few thousand light-years even with the extraordinary precision of the Gaia satellite. Beyond that distance, distances must be estimated from the physical properties of the stars, which requires knowing what type of star is being observed and how luminous that type of star is. The third obstacle is our motion. We are not stationary observers looking out at a static scene. We are in motion at 220 kilometers per second around the galactic center, and everything else in the galaxy is also in motion. Measuring the positions and velocities of stars does not immediately tell us the structure they collectively form, any more than watching a crowd of people moving through a city block immediately tells you the map of the city. Converting observed positions and velocities into a structural map requires models of the galactic potential and assumptions about how stars orbit within it. The analogy that most helpfully captures the Milky Way mapping problem is this. Imagine trying to draw a complete and accurate floor plan of a building in which you are confined to a single room with walls made of frosted glass. You can see shapes through the glass but they are blurred. You can hear sounds that give information about the layout. You can measure the time it takes for echoes to return from different directions. From all of this indirect evidence, you must infer the complete floor plan of a building you can never directly observe. Now imagine that the building contains 1 trillion rooms, most of them separated by walls so thick that even your best sensors can barely penetrate them, and that the building itself is in motion in complex ways that you must account for in interpreting everything you measure. The history of galactic mapping is a history of finding better ways to penetrate the frosted glass. The shift from visible light to radio waves allowed astronomers to hear what the glass blocked from sight. The shift to infrared allowed partial transparency where visible light found only opacity. The shift to measuring the actual positions and motions of 1 billion stars with the Gaia satellite provided a flood of information about the nearby structure that had previously been inferred only statistically. Each new observational capability has revealed both new detail in the known structure and new features that the previous, less capable surveys had missed entirely. The resulting map is now detailed and well calibrated for the immediate galactic neighborhood within a few thousand light-years. It becomes progressively less complete and less precise at larger distances, where dust and depth effects limit what can be observed, and where the indirect methods used to probe the distant galaxy carry larger systematic uncertainties than the direct Gaia parallax measurements that anchor the local picture. The Milky Way is a barred spiral galaxy, classified as type SBBC in the standard Hubble morphological sequence. This description packs a significant amount of structural information into a compact label, and unpacking it reveals the three-dimensional architecture within which the solar system is embedded. The spiral designation means that the galaxy has a disk of stars, gas, and dust in which higher density regions are organized into spiral arm patterns emanating from the central region. This disk is roughly flat, though as we will discuss later it is warped in the outer regions, and it is where essentially all active star formation in the galaxy is occurring. The disk has a diameter of approximately 100,000 to 120,000 light-years, though the exact value depends on how you define the disk's edge, which fades gradually rather than ending sharply. The barred designation refers to the central structure of the galaxy. Rather than the spiral arms emerging directly from a round central nucleus, As in a pure spiral galaxy, the Milky Way has a bar-shaped stellar structure extending from the center, with the spiral arms originating from the ends of this bar. The bar is roughly 27,000 light-years long, oriented at an angle of approximately 44 degrees to the line connecting the Sun to the galactic center. The bar is composed primarily of older stars with relatively lower gas content, and it rotates as a rigid body at an angular velocity different from the surrounding disk. The BC designation describes the tightness of the spiral arms and the relative prominence of the central bulge. The B component indicates moderately open spiral arms, with the C indicating that the central bulge is relatively small compared to the disk, which is characteristic of a galaxy where most of the mass and most of the star formation are in the disk rather than concentrated toward the center. The Milky Way has 4 major spiral arms, named the Norma, Scutum Centaurus, Sagittarius and Perseus arms, plus several shorter features and spurs. The arms are not solid structures moving through the disk like spokes of a wheel. They are patterns of density, regions where the gas and stars are somewhat more concentrated than in the interarm regions, and they persist because of density wave dynamics rather than because the same material stays in the arm indefinitely. Individual stars and gas clouds orbit through spiral arms, spending time in the higher density arm region and then continuing out into the interarm regions, like cars passing through a traffic jam rather than being part of the jam itself. The classification of the Milky Way as a barred spiral rather than a pure spiral was not established until relatively recently in astronomical history, because the bar is not visible in optical observations from our position inside the disk. The bar lies entirely within the inner galaxy, at galactic radii smaller than the solar orbit, and the dust extinction toward the galactic center made any bar invisible to optical surveys. Its existence was inferred from the dynamics of gas and stellar orbits in the inner galaxy, particularly from asymmetric gas velocities that suggested the influence of a non-axisymmetric mass distribution, and then confirmed directly by infrared surveys in the 1990s. The fraction of disk galaxies that are barred, as observed in surveys of external galaxies, is roughly 2/3 when imaging is sufficiently deep and the galaxy inclination allows bar detection. This high bar fraction suggests that bar formation is a natural outcome of disk galaxy dynamics rather than an exceptional structural feature. Bars form through gravitational instabilities in dynamically cold stellar disks and, once formed, can persist for billions of years. They play an important role in driving gas toward the galactic center, fueling star formation in the inner disk and potentially feeding the central black hole. The Milky Way's bar is not perfectly rigid or static. Numerical simulations of barred spirals show that bars evolve over time, their length and angular speed changing in response to interactions with the surrounding disk and dark matter halo. The bar may have been longer or shorter in the past, and its current properties reflect billions of years of dynamical evolution. The bar also drives resonances between the bar's rotation rate and the orbital periods of stars at specific galactic radii, creating rings and other structural features in the inner disk that are distinct from the spiral arms. The mass of the visible Milky Way, including stars, gas and dust, is estimated at roughly 100 billion solar masses in stars plus an additional 10 to 15 billion solar masses in gas and dust. The distribution of this mass across the structural components is uneven. The disk contains roughly 60 to 70% of the total stellar mass, the bulge and bar another 20 to 30%, and the stellar halo a small remainder of 1 to 2%. The precise apportionment depends on how the boundaries between components are defined in the models used to fit the observed stellar density distribution. The solar system is not located within one of the 4 major spiral arms of the Milky Way. It sits in a smaller structure, the Orion arm or Orion spur, sometimes also called the local arm, which is a shorter, spur-like feature connecting the Perseus arm on the outside to the Sagittarius arm on the inside. This intermediate position, between rather than within the major arms, has significant implications for the environment the solar system inhabits and has historically contributed to the difficulty of understanding the Milky Way spiral structure. The Orion arm is named for the constellation Orion and its surrounding region, which contains many of the most prominent nearby star-forming regions including the Orion Nebula, the Orion Molecular Cloud, and a complex of star-forming sites that define the brightest nearby portion of this structure. The arm or spur is roughly 10,000 light-years in length as currently estimated and extends in a direction roughly consistent with connecting the inner and outer major arms. For a long time, the Orion arm was classified as a minor spur or bridge structure rather than as a significant arm feature, largely because its observed length and density seemed insufficient to qualify it as a major arm comparable to Sagittarius or Perseus. However, more recent analysis using the precise astrometry from the Gaia satellite and from maser parallax measurements made by radiotelescope arrays including the Very Long Baseline Array has extended the observed length of the Orion arm and increased its estimated importance in the overall arm structure. Some current assessments suggest the Orion arm is genuinely a major arm feature that had been underestimated because our position within it makes it harder to observe as a coherent structure. The Solar System's position within the Orion arm is in the inner portion, closer to the Sagittarius arm than to the Perseus arm. The nearest portions of the Sagittarius arm are roughly 6,500 light-years inward of the Sun, while the Perseus arm begins at roughly 6,000 light-years outward. The Sun is thus genuinely between the two major arms, in a region where the average stellar density is somewhat lower than in the arm cores and where the rate of energetic events including supernova explosions is correspondingly lower. This interarm position is not merely a map coordinate. It has physical consequences for the solar system's environment. Supernova explosions, which can sterilize nearby planetary systems through gamma-ray and cosmic ray radiation, are more frequent near massive star-forming regions concentrated in the major spiral arms. An interarm location provides a degree of protection from the most energetically violent galactic events, and this protection has been proposed as one of the factors that made Earth's 4-billion-year biological history possible. The naming convention for galactic structures reflects the historical accident that they were first identified through prominent features visible from Earth. The Orion arm is named for the Orion Nebula and the Orion Molecular Cloud, which are among the most prominent nearby star-forming regions and whose association with a coherent arm-like structure was recognized early in the era of radio and optical arm tracing. Other arm segments and spurs are named for the constellations in which their most prominent associated HII regions appear in the sky. The Sagittarius arm for the prominent HII regions in Sagittarius, the Perseus arm for the giant molecular clouds in Perseus, and so on. The coherence of the Orion arm as a single structure extending thousands of light-years has been confirmed by maser parallax measurements from the VLBI Exploration of Radio Astrometry Program, VERA, and from the Bar and Spiral Structure Legacy Survey, BESSEL. These programs have measured precise parallaxes and proper motions for masers associated with high-mass star-forming regions throughout the galactic plane, placing individual star-forming complexes in a precise three-dimensional framework. The result is a map of star-forming regions in the Milky Way disk with precision comparable to what Gaia provides for individual stars, but extending much further through the disk by using masers that are intrinsically bright enough to be detected across large fractions of the galaxy. The Sun is located in the inner part of the Orion arm, at a position roughly consistent with the arm's local pitch angle and width. The pitch angle of the Orion arm is estimated at roughly 11 to 12 degrees, similar to the pitch angles of the major spiral arms, which supports the interpretation that the Orion arm is a genuine arm-like feature rather than just a chance alignment of nearby star-forming regions. Of all the measurements required to establish where we live in the Milky Way, the distance from the solar system to the galactic center is both the most fundamental and the one with the most dramatic history of revision. The current best value, approximately 26,000 light-years or 8,122 parsecs, is known to within about 2%, but arriving at this precision required more than a century of increasingly sophisticated observations and the resolution of a deep conceptual error that led early astronomers to place the Sun much closer to the center than it actually is. The first serious attempt to map the Milky Way and determine the Sun's position within it was made by William and Caroline Herschel in the late 18th and early 19th centuries. Their method was star counting. They assumed that all stars are intrinsically similar in brightness and that by counting how many stars appear in each direction of the sky, they could determine the shape of the stellar system and the Sun's position within it. Their analysis placed the Sun near the center of a flattened lens-shaped distribution of stars, consistent with the Milky Way appearing as a band of light encircling the sky from any location within the disk. The Herschels were wrong about the Sun being near the center, but for a reason they could not have known: interstellar dust. Because dust absorbs light preferentially at shorter wavelengths, and because the density of dust increases toward the galactic center, star counts based on visible light dramatically underestimate the number of stars toward the galactic center relative to the true distribution. The dust obscures most of the galaxy's stars and makes the visible universe appear centered on the Sun even though the Sun is in fact far from the center. The recognition that the Sun is far from the galactic center came from Harlow Shapley's work on globular clusters in the early 20th century. Globular clusters are densely packed spherical collections of old stars, orbiting the galaxy in the halo region above and below the disk. Because globular clusters orbit the galaxy's gravitational center, their spatial distribution should be roughly symmetric about that center. Shapley measured the distances to numerous globular clusters using Cepheid variable stars as standard candles and found that their distribution was not centered on the Sun but on a point roughly 65,000 light-years away in the direction of Sagittarius. Shapley's estimate of 65,000 light-years was too large by a factor of about 2.5, primarily because he did not account for the reddening of Cepheid light by dust, which made them appear fainter and therefore more distant than they actually were. But the qualitative conclusion, that the Sun is far from the galactic center and not at a special location within the disk, was correct and was a major conceptual revolution. The current best measurement of the Sun's distance from the galactic center comes primarily from two independent techniques that have reached a consensus. The first uses the orbits of stars near Sagittarius A** to determine the gravitational center of the galaxy and the distance from the Sun at which that center is located. The two groups that measured S2's orbit and confirmed the SGR A** black hole, Genzel's group and Geza's group, both reported the galactic center distance as a byproduct of their orbital analyses, finding values consistent with approximately 26,000 to 26,700 light-years. The second major technique uses the properties of stellar populations whose distances can be estimated from standard candle methods, including RR Lyrae variable stars and red clump giants, to trace the center of the galactic bar and bulge, which is coincident with the gravitational center. The International Astronomical Union defined the value of R0, the galactic center distance, as 8,500 parsecs in 1985 based on the best available data at the time. Subsequent measurements consistently found smaller values, and the current IAU recommended value has been updated to 8,122 parsecs, or approximately 26,500 light-years, reflecting the improved precision of current observations. The 2% precision on R0 is remarkable considering the indirect nature of the measurement and the dust that obscures the galactic center. The uncertainty is now dominated by systematic effects in the distance calibrations of the standard candles used, rather than by statistical measurement uncertainty, and further improvements will require either independent techniques or better calibration of the existing methods using parallax anchors from Gaia. The distance R0 to the galactic center is the fundamental unit that calibrates all other distance measurements within the Milky Way. When astronomers quote the distance to a globular cluster, a molecular cloud, or a spiral arm feature in the galaxy, that distance is ultimately based on the calibration chain that ties it to R0. The 2% precision now achievable for R0 therefore propagates into improved precision for all these derived distances, making the accurate determination of R0 the single most important measurement for understanding the galaxy's internal scale. The Solar System orbits the galactic center at approximately 220 kilometers per second, a speed determined by the gravitational pull of the roughly 10 to the 11 solar masses of stars, gas, dust, and dark matter enclosed within our orbit. This velocity, maintained over the Solar System's approximately 4.6 billion-year lifetime, means we have completed about 20 full orbits of the galaxy since the Solar System formed, a fact that provides useful context for galactic history. One complete galactic orbit, sometimes called a cosmic year or galactic year, takes approximately 225 to 250 million years. This unit is useful for describing events on galactic timescales in an intuitive way. In the last cosmic year, dinosaurs were just beginning their reign over Earth when the last cosmic year started, the Cretaceous period was still in the future, and modern mammals did not exist. 2 cosmic years ago, the most complex life on Earth was primitive marine invertebrates of the Cambrian period. 20 cosmic years ago, the galaxy itself was about 1/3 its current age and the first stars had only recently formed. The orbit of the Solar System around the galactic center is not a simple circular path. It has a modest eccentricity, meaning the Solar System moves slightly closer to and farther from the galactic center over each orbit. Additionally, the Solar System oscillates up and down through the galactic plane, crossing through the midplane approximately every 32 to 35 million years and reaching maximum elevations of about 230 light-years above or below the plane. This oscillation is superimposed on the circular orbital motion and means the Solar System traces a gentle helical path through the galaxy rather than a flat circle. The oscillation through the galactic plane has attracted scientific attention because the galactic midplane is where the density of molecular clouds, massive star-forming regions, and therefore supernova explosions is highest. Each time the Solar System passes through the midplane, it spends time in a higher density, more energetically active region of the disk. Some researchers have proposed that the 32 to 35 million-year period of plane crossing correlates with periodic increases in comet bombardment of the inner Solar System, as the gravitational perturbation of the dense midplane disturbs the Oort cloud and sends more comets inward. Whether this correlation is real and causally significant remains debated, but the geometry of the oscillation is well established. The speed of 220 km per second at our galactic radius provides a baseline against which the motions of other objects in the galaxy are measured. The peculiar velocities of nearby stars, their velocities relative to the local standard of rest defined by the average motion of stars in the solar neighborhood, are typically tens of kilometers per second. The Sun's own peculiar velocity, the component of its motion that deviates from the average circular orbit, is about 13 kilometers per second toward the constellation Hercules, a motion called the solar apex. The question of whether the solar system's galactic orbit has been stable over its lifetime, maintaining approximately the same galactic radius and roughly circular eccentricity, is important for assessing the galactic environment that Earth has experienced over its history. If the solar system had spent time at significantly different galactic radii, the environment would have been different. Closer to the center means higher stellar density, higher radiation, and more frequent close encounters with other stars. Farther from the center means lower metallicity and different galactic chemical evolution. Current models of galactic dynamics, constrained by the observed properties of the solar neighborhood stellar population, suggest that the Sun's galactic orbit has been reasonably stable over the past several billion years, with radial oscillations of perhaps a few thousand light-years about the mean radius of 26,000 light-years. This is not perfectly circular, but it is sufficiently stable that the Sun has remained within the general region of the galaxy that constitutes the proposed galactic habitable zone throughout the time that complex life has existed on Earth. The angular position within the galaxy, which spiral arm the solar system is currently near, and what the local arm structure looks like, has changed more significantly over the history of the solar system due to the differential rotation between the Sun's orbital speed and the spiral arm pattern speed. This differential rotation, the fact that the Sun orbits faster than the spiral arms rotate, means that the Sun has overtaken or been overtaken by spiral arms multiple times in its history, periodically entering arm regions and then departing into interarm space again. At the heart of the Milky Way, within the innermost few thousand light-years, the galactic structure is dominated by two related components that are distinct from the surrounding disk: the central bar and the central bulge. Understanding these structures and their relationship to our location is important because they define the gravitational environment of the inner galaxy, and they represent a fundamentally different mode of galactic organization from the disk we inhabit. The galactic bar is a cigar-shaped concentration of stars extending from the galactic center outward in two directions, aligned at approximately 44 degrees to the line from the Sun to the galactic center. The bar is roughly 27,000 light-years in total length, meaning it extends about 13,500 light-years from the center in each direction. Unlike the disk, which has ongoing star formation, the bar is composed predominantly of older, redder stars with relatively little gas and low current star formation rates. The bar is dynamically significant because it rotates as a near-rigid body, driving gas flows in the inner galaxy and influencing the structure of the inner spiral arms. The bar was detected through infrared observations in the 1990s, after earlier radio and optical observations had provided hints of asymmetric structure near the galactic center. Infrared light penetrates dust much more effectively than visible light, allowing the star distribution of the inner galaxy to be mapped without the severe obscuration that hampers visible light observations toward the center. When the stellar density was mapped in the infrared, a distinctly asymmetric distribution was apparent, with the near end of the bar at positive galactic longitudes appearing brighter than the far end at negative longitudes, exactly as expected if the bar's near end is closer to us than the far end. The central bulge is the roughly spheroidal concentration of stars at the galactic center that is distinct from both the disk and the bar. The bulge is sometimes described as if it were a simple featureless sphere of old stars, but modern observations have shown it to be more complex. It has a peanut-shaped or boxy morphology when viewed from outside, consistent with it being a bar that has buckled vertically due to dynamical instability. The peanut shape is visible in the distribution of red clumped giant stars, which are standard candles that can be used to trace the three-dimensional structure of the bulge. The bulge contains a mix of stellar populations, including both very old stars more than 10 billion years old and more recently formed stars, with the mix varying with position within the bulge. Its total stellar mass is estimated at roughly 1 to 2 times 10 to the 10 solar masses, comparable to the total stellar mass of the disk, making it a significant component of the galaxy's total stellar budget. The distinction between the bar and the bulge was not always recognized, and older models of the galactic center described a single featureless spheroidal bulge rather than the boxy, peanut-shaped structure now known to exist. The recognition that the bulge has a boxy morphology came from infrared surveys in the 1990s and 2000s that revealed asymmetric number counts and distance distributions of bulge stars, inconsistent with a smooth spheroid but consistent with a bar viewed at an angle from within the disk. The peanut shape of the bulge, visible when the galaxy is viewed edge-on from an external vantage point, arises from a dynamical process called buckling instability. When a bar forms and persists for long enough, the stars oscillating vertically through the bar can develop orbits that take them significantly above and below the midplane, creating the characteristic swelling in the middle that produces the peanut or boxy shape. Simulations of barred galaxy evolution routinely produce this morphology, and observations of external edge-on galaxies show that boxy bulges are common among barred spirals. The stellar populations of the bulge are heterogeneous. The dominant component is old, metal-rich stars, but observations with the VLT, Keck, and Hubble telescopes have revealed a complex mix with significant numbers of intermediate-age stars and a wide range of metallicities. This complexity suggests that the bulge formed not in a single rapid event but through multiple phases of star formation, including contributions from the early rapid buildup of the galaxy's inner regions and from material redistributed inward by the bar. Understanding the detailed formation history of the galactic bulge remains one of the active problems in Milky Way research. At the gravitational center of the Milky Way, approximately 26,000 light-years from the Solar System in the direction of the constellation Sagittarius, sits one of the most extreme physical environments in the galaxy. The galactic center is a region of extraordinary stellar density, intense electromagnetic radiation, complex gas dynamics, and at its very heart, a supermassive black hole with a mass of approximately 4 million solar masses named Sagittarius A star. The galactic center cannot be observed at visible wavelengths from Earth. The column of interstellar dust between the solar system and the galactic center is so thick that it extinguishes visible light by a factor of roughly 10 to the 27th, making the galactic center optically invisible even with the most powerful telescopes. Observations of the galactic center require radio wavelengths, which pass through dust essentially unimpeded, and infrared wavelengths, which are attenuated by only a few magnitudes rather than the dozens of magnitudes suffered by visible light. X-ray and gamma-ray observations reveal the energetic processes associated with the supermassive black hole and with the dense stellar environment. Sagittarius A*, the compact radio source at the galactic center, was first detected in 1974 by radio astronomers Bruce Ballack and Robert Brown. Its compactness, variability, and the extraordinary concentration of mass implied by the orbital velocities of nearby stars immediately suggested it was associated with a massive black hole, but establishing this beyond doubt required decades of patient observation. The definitive evidence came from tracking the orbits of individual stars very close to the galactic center, a project pursued by two independent groups. One led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics and one led by Andrea Ghez at UCLA. Both groups, using near-infrared adaptive optics on the largest ground-based telescopes, tracked dozens of stars for more than 20 years and determined their complete orbits around the central concentration of mass. The star S2, the most extensively tracked, has an orbital period of approximately 16 years and a closest approach to the galactic center of only about 120 astronomical units, at which point it reaches speeds of nearly 7,650 km per second. The mass enclosed within S2's orbit, determined from the orbital period and size by exactly the same method Kepler used to determine planetary masses in the Solar System, is approximately 4 million solar masses, all contained within a radius of roughly 120 astronomical units. The only physically plausible explanation is a supermassive black hole. The environment within the central parsec of the Milky Way, the region immediately surrounding Sagittarius A*, is one of the densest and most dynamically extreme stellar environments in the galaxy. The stellar density within this region exceeds that of the solar neighborhood by a factor of roughly 1 million, meaning that stars there are separated by distances comparable to the size of the solar system rather than the light years that separate stars in our neighborhood. This density has consequences for the dynamical evolution of stellar orbits and for the probability of stellar collisions or tidal disruptions. The young massive stars found within a fraction of a parsec of SGR A*, the S-star cluster, are a puzzle for stellar physics. These stars, with spectral types indicating masses of 10 to 15 solar masses and ages of only a few million years, should not be able to form in the tidal environment of the galactic center, where the extreme gravity gradient from the central black hole tears apart any gas cloud before it can collapse to form stars. Their presence there has been called the paradox of youth and has been explained by various mechanisms including in situ formation in a dense disk of gas around the black hole, migration inward from larger radii, or formation in infalling massive star clusters that spiraled in through dynamical friction. SGR-A* itself, despite being a 4 million solar mass black hole, is remarkably quiet. It emits at a luminosity many orders of magnitude below the Eddington luminosity, the theoretical maximum luminosity for a black hole of its mass, meaning it is currently accreting material at an extremely low rate. This quiescence is consistent with the absence of any large reservoirs of cold gas immediately surrounding the black hole, but it contrasts sharply with the activity of galactic nuclei in other galaxies, raising the question of why our galactic center black hole is so inactive compared to its counterparts elsewhere. The Event Horizon Telescope collaboration produced the first image of a black hole's shadow in 2019, imaging the shadow of the supermassive black hole in the galaxy M87 at a resolution sufficient to resolve structure on the scale of the event horizon. A subsequent image of Sagittarius A*, published in May 2022, showed the shadow of the Milky Way's own central black hole for the first time, confirming its mass and the applicability of general relativity in the extreme gravitational environment of the galactic center. The SGR-A* image was more technically challenging than the M87 image because SGR-A* is much lower mass and therefore varies on much shorter timescales, requiring sophisticated time averaging techniques to produce a coherent image. The major spiral arms of the Milky Way are not uniformly distributed around the galaxy. They emerge from the ends of the central bar and wind outward through the disk, with the pitch angle, the angle between the arm and the tangent to a circle at that galactic radius, determining how tightly or loosely wound the arms are. For the Milky Way, the pitch angle is approximately 12 to 15 degrees, giving moderately open arms consistent with the SBBC morphological classification. The four major arms are named by the prominent stellar populations and HII regions they contain in the directions where they are most directly observable from the solar system. The Norma arm is the innermost major arm, lying between the galactic center and the solar orbit. The Scutum Centaurus arm is the next arm outward. The Sagittarius arm passes between the Sun and the galactic center at a distance of roughly 6,500 light-years from the solar system. The Perseus arm is the next major arm outward from the Sun, at roughly 6,000 to 7,000 light-years. The outer arm continues beyond Perseus. The solar system's position between the Sagittarius and Perseus arms places it in a region of the disk that is relatively less active than the arm cores. Spiral arms are the preferential locations for star formation in disk galaxies because the arm density waves compress gas clouds and trigger their collapse into new stars. In the major spiral arms, the concentration of newly formed massive stars, stellar nurseries, supernova remnants, and HII regions is high. In the interarm regions, the gas and stellar density is lower and the rate of energetic events correspondingly reduced. The galactic habitable zone concept, which we will discuss more fully in a later chapter, relies heavily on this arm versus interarm distinction. The argument is that the energetic events associated with the spiral arms, including the intense cosmic ray flux from nearby supernovae and the disruptive gravitational encounters with dense molecular clouds, would be harmful to the development and maintenance of complex life on any planet that spent much of its time within a major spiral arm core. An interarm position provides a degree of shelter. However, the relationship between spiral arms and stellar positions is not static. Stars move through the disk at velocities that are not exactly synchronized with the spiral arm pattern speed, which means that over millions of years, stars and their planetary systems pass through spiral arm regions multiple times. The solar system, over its 4.6 billion-year history, has passed through spiral arm regions, interarm regions, and back multiple times, with the potential environmental consequences of each passage depending on the density of the arm at the time of crossing. The pattern speed of the Milky Way spiral arms, the rate at which the spiral density wave rotates around the galactic center, is a quantity that has been difficult to measure precisely from within the galaxy. Estimates have varied widely, from roughly 20 to 30 km per second per kiloparsec, and the uncertainty has important consequences for understanding how the solar system interacts with the spiral pattern. If the pattern speed is close to the Sun's angular velocity, the Sun orbits with the spiral arms and spends an extended time near any given arm. If the pattern speed is substantially different, the Sun moves through the arm quickly. The corotation radius, the galactic radius at which stars orbit at exactly the same angular velocity as the spiral pattern, is a special location in the galaxy. At the corotation radius, stars neither gain nor lose energy from the spiral wave on average, and the interaction between the disk gas and the spiral pattern is qualitatively different from its behavior at other radii. Some studies have placed the corotation radius close to the Sun's galactic orbit, which if true would mean the solar system is near this special location where the arm-star interaction is minimal. Whether this proximity to corotation is coincidental or significant for the solar system's environment is debated. The interarm gaps between the Sagittarius and Perseus arms that bracket our position are not perfectly empty. Surveys of molecular gas and young stars show some concentrations in the interarm region, including the Orion arm itself and various smaller features. The arm-to-interarm contrast in gas density and star formation rate is real but not extreme, perhaps a factor of 2 to 5 in surface density rather than the factor of hundreds that would represent completely evacuated interarm space. The interarm environment is quieter than the arm cores but not categorically different. The solar system is currently embedded within a structure called the local bubble, a roughly spherical region of hot, low-density gas that extends roughly 300 to 600 light-years in most directions from the Sun. This bubble is a cavity in the otherwise denser interstellar medium, and it has significant consequences for the heliosphere, for the cosmic ray environment of the solar system, and for the visibility of nearby stars. The local bubble is hot. The gas filling it has a temperature of approximately 1 million Kelvin, heated by the energy of past supernova explosions that excavated the cavity. Despite this high temperature, the gas is so diffuse, with a density of only about 0.005 atoms per cubic centimeter compared to a typical interstellar value of about 1 atom per cubic centimeter, that the thermal energy per unit volume is low and the gas does not radiate efficiently in the visible. Instead, it emits soft X-rays, and the diffuse soft X-ray background seen all over the sky corresponds largely to this hot local bubble gas. The bubble is not perfectly round and its boundaries are not sharp. In some directions, the boundary occurs where the hot, low-density bubble gas meets the denser, cooler gas of the surrounding medium, and in those directions the transition is marked by walls of molecular clouds and higher-density neutral gas. In other directions, the bubble connects to other cavities, forming a network of interconnected voids called the local chimney or other structures that extend high out of the galactic plane. The most likely origin of the local bubble is a series of supernova explosions that occurred within a moving group of stars called the Scorpio-Centaurus OB association, the nearest OB association to the solar system. Over the past 10 to 20 million years, roughly 15 to 20 supernova explosions from this association are estimated to have occurred, each one adding energy to the expanding cavity. The association itself has moved away from the bubble as the solar system orbited through the region, and what remains is the hot gas filling the evacuated space. The local bubble has direct consequences for the solar system's environment. The transition from the dense interstellar medium to the hot, low-density bubble occurs at the bubble's boundary, and the heliosphere, the region dominated by the solar wind, is shaped by the pressure of the external medium. In the denser medium outside the bubble, the heliosphere would be compressed to a smaller size. Within the bubble's low-density gas, the heliosphere expands to a larger volume, providing somewhat more shielding for the inner solar system against galactic cosmic rays. The boundary of the local bubble is traced by the sudden increase in dust extinction and neutral hydrogen column density that occurs when observations cross from the hot, low-density interior to the denser interstellar medium outside. This boundary is approximately 100 to 300 light-years from the Sun in most directions, though it extends farther in some directions where the bubble connects to other low-density structures. The local bubble is not isolated. It connects to several other cavities in the local interstellar medium, forming a complex of interconnected low-density regions sometimes called the local chimney, which extends to high galactic latitudes where the hot gas can leak out of the disk into the galactic halo. The Scorpio-Centaurus superbubble, a region of hot gas associated with the active star formation and recent supernova history of the nearest OB association, is adjacent to the local bubble and may be connected to it through a thin waste of low-density gas. The age of the local bubble, estimated at roughly 10 to 20 million years based on the time required for the supernova explosions that created it, coincides with a period of enhanced supernova activity from the Scorpio-Centaurus association. During this period, the solar system was at a different position in its galactic orbit and was not yet in the region that became the local bubble. The solar system entered the local bubble within the past few million years as it moved through the region where the bubble had already been excavated. This transit of the solar system into the hot, low-density local bubble environment may have changed the properties of the heliosphere and therefore the cosmic ray environment at Earth's surface in ways that could have subtle but detectable influences on geological or biological history. The recent evidence that the Sun entered the local bubble within the past few million years has been strengthened by analyses of iron-60 in deep-sea sediments and in lunar samples. Iron-60 is a radioactive isotope with a half-life of about 2.6 million years that is produced in supernova explosions and distributed into the surrounding interstellar medium. Its presence in deep-sea sediments at elevated concentrations, measured by several research groups, provides a record of nearby supernova activity over the past few million years and is consistent with the series of supernovae from the Scorpio-Centaurus Association that created and maintained the local bubble. The galactic disk is not a single homogeneous structure. It consists of at least two distinct components with different stellar populations, different vertical extents, and different kinematic properties, overlaid to produce the disk we observe. Understanding the distinction between these components is essential for understanding the solar system's specific position within the disk. The thin disk is the component that contains most of the current star formation, most of the gas, and most of the young and intermediate-age stellar populations. It has a vertical scale height of roughly 300 to 400 light-years, meaning the density of thin disk stars decreases by a factor of E roughly every 300 to 400 light-years above or below the midplane. The Sun is located in the thin disk, at a height of approximately 50 to 100 light-years above the midplane. This small elevation above the strict midplane is within the normal range for thin disk stars and has no special significance. The thin disk is the source of essentially all ongoing star formation in the galaxy. The molecular clouds from which new stars form are concentrated in the thin disk's midplane, and the spiral arm structure that organizes star formation is a thin disk phenomenon. The youngest and most massive stars, the O and B-type stars whose ionizing radiation produces HII regions and whose eventual deaths as supernovae drive the next round of star formation and feedback, are exclusively thin disk objects. The thick disk is an older, kinematically hotter component that extends to significantly larger heights above and below the midplane, with a scale height of roughly 1,000 light-years. Thick disk stars are systematically older than thin disk stars, typically more than 8 billion years old, and they have lower metallicities, meaning they formed when the interstellar medium had been less enriched by previous generations of stellar nucleosynthesis. The thick disk is thought to have formed early in the galaxy's history, perhaps through a period of chaotic star formation before the thin disk settled into its current dynamically cool configuration, or through the heating of an original thin disk by the accretion of satellite galaxies. The outer disk of the Milky Way is warped, a feature detected in observations of atomic hydrogen and more recently in stellar surveys including Gaia. The warp means that the outer disk is not flat but curls upward on one side of the galaxy and downward on the other, like the brim of a hat that has been pushed from below on one side. The solar system is in the inner portion of the disk where the warp is minimal, but at galactic radii significantly larger than the solar orbit, the displacement of the disk from the midplane reaches several thousand light-years. The chemical distinction between the thin and thick disk populations is one of their most diagnostic properties and one that provides a window into the star formation history of the galaxy. Thin disk stars span a wide range of metallicities and include both relatively metal-poor old stars and very metal-rich young stars, reflecting ongoing star formation over a long period in a chemical environment that has been progressively enriched. Thick disk stars are predominantly metal-poor relative to thin disk stars of the same age, consistent with formation in the early galaxy before significant chemical enrichment had occurred. The alpha-to-iron ratio provides an additional chemical clock for distinguishing disk populations. Alpha elements, those produced primarily by core-collapse supernovae of massive stars that explode on short timescales, include oxygen, magnesium, silicon, and calcium. Iron is produced primarily by type Ia supernovae, which explode from binary star systems on timescales of hundreds of millions to billions of years. Stars that formed early, when the interstellar medium had been enriched only by rapid core-collapse supernovae, have high alpha-to-iron ratios. Stars that formed later, after type Ia supernovae had added iron to the medium, have lower alpha-to-iron ratios. The bimodal distribution of disk stars in alpha-to-iron versus metallicity space is one of the clearest observational signatures of the distinction between the old, rapidly formed thick disk and the younger, slowly evolved thin disk. The galactic warp is most prominent beyond the solar galactic radius. At radii of 40,000 to 60,000 light-years, the disk is displaced from the midplane by several thousand light-years in the warped regions. The physical cause of the warp is not definitively established, with proposed mechanisms including gravitational perturbation from the Magellanic Clouds, misalignment between the disk and the dark matter halo, and intergalactic gas infall. Beyond the galactic disk, both above and below the plane and extending in a roughly spheroidal distribution to distances of several 100,000 light-years, lies the galactic stellar halo. The halo is sparsely populated with stars, contributing perhaps 1 to 2% of the galaxy's total stellar mass, but its stars carry important information about the Milky Way's assembly history, and they provide key reference points for determining the galaxy's total mass and extent. The stellar halo is composed predominantly of very old, metal-poor stars, the chemical composition of which reflects formation in the early universe when the interstellar medium had not yet been enriched by many generations of stellar nucleosynthesis. These stars are remnants of either the earliest stages of the Milky Way's own formation or the remnants of smaller satellite galaxies that have been absorbed and disrupted by the Milky Way's gravitational field over the past several billion years. The distinction between halo stars that formed in the Milky Way and those that formed in accreted satellites is now becoming possible through the exquisite kinematic data provided by the Gaia satellite. Stars from the same progenitor satellite tend to move with similar velocities through the galaxy, forming kinematic substructures and velocity space that persist long after the spatial coherence of the original satellite has been erased by tidal disruption and phase mixing. The most significant accreted component identified so far is the Gaia Enceladus sausage, a galaxy whose mass was comparable to the Large Magellanic Cloud that merged with the Milky Way roughly 8 to 10 billion years ago and contributed a substantial fraction of the current interstellar halo. Globular clusters are among the most spectacular objects in the galaxy and the ones that proved most useful for establishing the Sun's position within the Milky Way. These compact, spherical collections of stars, each containing between 10,000 and several million members, orbit the galaxy in the halo at typical distances of tens of thousands of light-years. The Milky Way contains approximately 150 known globular clusters, though the true number may be somewhat higher with some clusters hidden behind the galactic plane's dust. The distribution of globular clusters on the sky is not centered on the Sun. It is strongly concentrated toward the constellation Sagittarius and toward the inner galaxy, a reflection of the fact that the cluster's center of distribution is the galactic center rather than the solar system. It was precisely this asymmetry in globular cluster distribution that allowed Shapley to determine that the Sun is not at the galaxy's center, the foundational observation that transformed our understanding of the Milky Way structure. The globular cluster system of the Milky Way has been studied extensively as a tracer of the galaxy's formation history. The clusters span a range of ages from roughly 10 to 13 billion years and a range of metallicities from extremely metal-poor, with iron abundances 100 times below solar, to moderately metal-rich. This spread in properties suggests that the globular clusters were not all formed in the same epoch or in the same environment. Some formed in the early Milky Way itself, while others formed in satellite galaxies that were subsequently accreted. The distinction between in situ and accreted globular clusters has become clearer with the Gaia kinematic data, which allows the orbits of clusters throughout the halo to be determined and compared with theoretical predictions for clusters formed in satellites versus those formed in the main galactic progenitor. Clusters associated with the Gaia Enceladus sausage merger have been identified through their kinematic signature, as have clusters associated with other named merger events in the galaxy's history. For our understanding of where we live in the galaxy, globular clusters serve as a reference population that is distributed throughout the three-dimensional volume of the galactic system rather than confined to the disk. Their distribution defines the extent and shape of the galaxy's gravitational potential in a way that disk surveys cannot, extending the mapping of the galaxy from the two-dimensional disk to the three-dimensional spheroid that encompasses it. The globular cluster system also provides the longest historical record of stellar populations in the galaxy, with the oldest clusters preserving the chemical and dynamical signatures of conditions in the galaxy more than 13 billion years ago. The concept of a galactic habitable zone, the region within the Milky Way where conditions are most conducive to the development and long-term maintenance of complex life, was formalized by Guillermo Gonzalez, Donald Brownlee, and Peter Ward in the early 2000s. The idea extends the familiar concept of the stellar habitable zone, the region around a star where liquid water can exist on a planet's surface, to the galactic scale, asking which parts of the galaxy are most suitable for the overall conditions that complex biospheres require. The galactic habitable zone is proposed to be an annular region at intermediate galactic radii, roughly 22,000 to 30,000 light-years from the galactic center, with the Sun sitting comfortably near the middle of this range. The inner boundary is set by several factors that make the inner galaxy hostile to complex life. The density of stars increases steeply toward the galactic center, increasing the rate of gravitational perturbations of cometary reservoirs, potentially triggering episodes of intense comet bombardment. The radiation environment is more intense, with higher fluxes of X-rays and gamma rays from the active processes near the galactic center. The frequency of supernova explosions is higher in the more metal-rich, actively star-forming inner galaxy. The outer boundary of the galactic habitable zone is proposed to be set by the decreasing metallicity of stars and their planetary systems at large galactic radii. Metallicity in astronomy refers to the abundance of elements heavier than hydrogen and helium, elements produced by stellar nucleosynthesis and distributed through the interstellar medium when stars die. In the outer galaxy, where fewer generations of star formation have occurred and the interstellar medium has been less chemically enriched, the average metallicity of newly forming stars is lower. The relevance of metallicity to habitability is that rocky planets, the kind on which surface life as we know it is possible, are made of heavy elements including iron, silicon, magnesium, oxygen, and various others. A stellar system with very low metallicity may not have enough heavy elements to form Earth-mass rocky planets at all. Even if it does form rocky planets, they may have different internal structures and geological activity from Earth due to different abundances of heat-producing radioactive elements like thorium and uranium. The solar system sits at a galactic radius where the metallicity is high enough to form rocky planets with Earth-like composition but not so high that the inner galaxy's hazardous environment applies. This appears to be a meaningful aspect of the solar system's location, though how wide the galactic habitable zone actually is, and how the various proposed inner and outer boundary mechanisms actually operate, remains an area of active research. The metallicity gradient of the Milky Way disk, the decrease in the average metallicity of stars with increasing galactic radius, provides one of the most quantitative constraints on the galactic habitable zone's outer boundary. The gradient is approximately -0.06 dex per kiloparsec in the disk, meaning that for every additional kiloparsec of galactic radius, the average metallicity of disk stars decreases by about 14%. At twice the solar galactic radius, approximately 52,000 light-years, the average metallicity is roughly 40% below solar. Whether this reduction is sufficient to significantly impair rocky planet formation is uncertain, as planet formation models suggest that Earth-mass rocky planets can form at metallicities well below solar, but the internal composition and heat budget of such planets would differ from Earth's. The rate of supernova explosions as a function of galactic radius provides the primary quantitative argument for the inner boundary of the habitable zone. The supernova rate in the inner galaxy, within perhaps 15,000 to 20,000 light-years of the center, is estimated to be several times higher than in the solar neighborhood, reflecting both the higher star formation rate and the higher density of massive star-forming regions. A supernova within roughly 30 light-years of a planetary system would deliver a dose of gamma rays and cosmic rays potentially sufficient to cause significant biological damage. The frequency of such events in the solar neighborhood is estimated at perhaps one every several hundred million years, a rate that may be compatible with the long-term persistence of complex life. In the inner galaxy the rate would be higher. The galactic habitable zone concept has been criticized for being based on incomplete models of stellar distribution, supernova rates, and planet formation, and for assuming that life requires Earth-like conditions without considering alternative biochemistries that might function in different environments. These criticisms are valid, and the galactic habitable zone should be understood as a working hypothesis rather than an established fact. But the underlying physical arguments, that environment matters for planetary habitability at the galactic scale, are robust. The timing argument adds a temporal dimension to the galactic habitable zone concept. Not only must a planetary system be at an appropriate galactic radius, it must form at an appropriate cosmic epoch, after the interstellar medium has been sufficiently enriched with heavy elements to permit rocky planet formation, but before the conditions in the galaxy change in ways that would be unfavorable. The solar system formed at a cosmic age of roughly 9 billion years, a time when the interstellar medium at the solar galactic radius had reached the metallicity appropriate for forming an Earth-like planet with the right proportions of heat-producing radioactive elements, silicate mantle, iron core, and water. The history of attempts to map the Milky Way from within it is a story of increasingly sophisticated methods, each generation revealing that the previous one had made systematic errors because it lacked the tools to account for some important complicating factor. Following this history illuminates both how the current picture was assembled and why confidence in it is now high in a way that it could not have been in previous eras. The Herschel star counting approach of the late 18th century described earlier placed the Sun near the center of the galaxy. The error arose from not knowing about interstellar dust, which makes distant stars appear faint and systematically reduces the count of stars and directions toward the dusty galactic midplane. Shapley's globular cluster mapping of the 1910s placed the Sun far from the galactic center but overestimated the distance by a factor of about 2.5 because early Cepheid distance calibrations did not account for the dimming and reddening of Cepheids by dust. Subsequent work by others, particularly Robert Trumpler's 1930 demonstration that interstellar absorption exists and is significant, led to a revised calibration of Cepheid distances that reduced the estimated galactic scale. Radio astronomy, which became available in the post-war period, opened a new window on galactic structure by allowing observations of the 21-centimeter emission from neutral hydrogen gas, which penetrates dust completely. Mapping the radial velocities and distances of hydrogen clouds throughout the galaxy using the 21 centimeters line provided the first clear evidence for the spiral arm structure of the Milky Way, tracing the arms by the distribution of gas rather than stars. Infrared surveys, particularly the 2-micron all-sky survey completed in 2001, provided the first comprehensive view of the stellar distribution in directions where dust extinction is severe, revealing the bar and bulge structures that are invisible in optical light. The Glimpse and Mipscall surveys from the Spitzer Space Telescope added detailed infrared maps of the inner galactic plane at higher resolution. The Gaia satellite represents the current state of the art in galactic mapping. By measuring the parallaxes of approximately 1.5 billion stars with microarcsecond precision, Gaia has produced the most complete and accurate three-dimensional map of the solar neighborhood and the Milky Way's disk within a few thousand parsecs. The velocity measurements Gaia provides, including proper motions and radial velocities for hundreds of millions of stars, are revealing the kinematic substructure of the disk and halo in unprecedented detail. The Vera and Bessel programs represent the current frontier in direct distance measurement to distant galactic features. By measuring the trigonometric parallaxes of water and methanol masers associated with high-mass star-forming regions, these programs have achieved astrometric precisions of 10 to 20 microarcseconds, comparable to Gaia's performance for individual stars. This precision allows parallax distance measurements to masers at distances of several kiloparsecs, placing the three-dimensional positions of dozens of high-mass star-forming regions in the galactic disk with direct geometric accuracy. The maser parallax measurements have had a dramatic impact on understanding the spiral arm structure of the inner Milky Way. Before these measurements, the positions of individual star-forming regions within the arm structure were inferred from kinematic distances, estimated from the radial velocities of associated molecular gas and the assumed rotation curve of the galaxy. Kinematic distances are subject to significant uncertainties related to non-circular gas motions, particularly in the inner galaxy where the bar drives strong departures from circular rotation. The direct maser parallaxes have shown that some kinematic distance estimates were wrong by significant factors. The synthesis of Gaia parallaxes for the nearby disk, maser parallaxes for more distant star-forming regions, and radio observations of the HI and CO gas distribution gives the most complete and accurate picture of the Milky Way structure ever assembled. It is a picture that still has gaps and uncertainties, particularly for the far side of the galactic disk beyond the center where dust obscuration is most severe, but it is now firmly anchored in direct distance measurements rather than relying entirely on models and indirect inferences. The ongoing Gaia mission, now in its extended phase, continues to refine the astrometric catalog with additional observation epochs that improve the parallax and proper motion precision for all sources. Each additional year of data reduces the parallax uncertainty by roughly the inverse square root of the number of epochs, meaning the catalog quality improves continuously as the mission extends. The Gaia data have also been used to identify stellar streams, clusters, and other kinematic groups that were undetectable in pre-Gaia data, revealing the accretion history of the Milky Way through the kinematic fossils left by disrupted satellite galaxies. Because we are embedded within the Milky Way and cannot observe it from the outside, our picture of what our galaxy looks like as a whole is assembled by combining all the available evidence about its structure into a coherent three-dimensional model, and then comparing that model with observations of other galaxies whose global properties we can assess from our external vantage point. The overall appearance of the Milky Way from outside would depend on the viewing angle. Seen face-on from directly above the galactic pole, the Milky Way would show a prominent central bar, surrounded by a slightly oval bulge, with four major spiral arms emerging from the bar ends and winding outward through the disk. The arms would be lit up by HII regions and young blue massive stars, while the interarm regions would be somewhat darker and redder. The total diameter of the visible disk would be roughly 100,000 to 120,000 light-years. Seen edge-on from within the disk plane, the Milky Way would appear as a flattened lens shape, brighter in the center where the bulge is and fading gradually toward the disk edges. The disk thickness, compared to its diameter, would be similar to a thin sheet of paper viewed edge-on, with the very thin dust lane visible as a dark band running along the midplane where the greatest concentration of dust lies. The comparison most commonly made is to galaxies like M31 Andromeda or M101 the Pinwheel Galaxy or NGC 1300, a prominent barred spiral, because these are large, well-studied galaxies whose morphological type roughly matches the Milky Way's. The comparison to NGC 1300 is particularly instructive for visualizing the bar structure, while the comparison to M31 illustrates what a large, bright central bulge looks like from outside when the viewing angle is comparable to our view of the Milky Way in projection. The Milky Way's total luminosity, integrated across all wavelengths, is approximately 20 to 25 billion times the luminosity of the Sun. Most of this luminosity comes from the stars of the disk and bulge, with the disk contributing roughly 2/3 of the total light and the bulge 1/3. In comparison to other galaxies in the local universe, the Milky Way is a large spiral, somewhat brighter than the median spiral galaxy but less luminous than the very largest examples. In the local group, the Milky Way and Andromeda are roughly comparable in mass and luminosity, with Andromeda perhaps slightly more massive, and both are dramatically larger than all other local group members. The comparison of the Milky Way to external barred spiral galaxies is complicated by the fact that we know the Milky Way's properties from inside, while we know external galaxies only from outside. The transition between these two perspectives requires combining the complementary information from both approaches. Internal observations give detailed structural information about the local environment and kinematic substructure, while external galaxy comparisons give context for the global properties and visual appearance that we cannot observe directly. The near-infrared luminosity of the Milky Way places it in a well-characterized region of the luminosity function of local spiral galaxies, useful for comparison with other spirals whose properties are known from photometric surveys. The rotation velocity of approximately 220 km per second places the Milky Way in the luminosity class of large spiral galaxies on the Tully-Fisher relation, which connects spiral galaxy rotation speed to luminosity. This places the Milky Way in a class with other large spiral galaxies such as M33 in the local group and many others in nearby galaxy groups. The Milky Way's color, the spectral energy distribution of its total stellar population, is characteristic of a galaxy with ongoing star formation at a moderate rate. It is bluer than a passive elliptical galaxy but redder than a vigorously star-forming starburst galaxy. The current star formation rate of the Milky Way is estimated at roughly 1 to 3 solar masses per year, modest by the standards of the galaxy's history but consistent with the declining but ongoing star formation expected for a galaxy that formed most of its stars several billion years ago and has been gradually exhausting its gas supply since. The specific view of the galaxy available from our location in the Orion Arm, at 26,000 light-years from the center, is shaped by our position in a way that has determined both the history of astronomical understanding and the specific observational challenges that astronomy has had to overcome. The most obvious consequence of our location is the Milky Way band visible in the night sky. Because the solar system is embedded in the disk appears as a band of concentrated starlight encircling the sky at the plane of the galactic equator. The band is brightest in the direction of the galactic center, in the constellation Sagittarius and surrounding regions, where the maximum concentration of stars lies along the line of sight. It is fainter in the direction of the galactic anticenter, opposite Sagittarius, where the disk thins toward the outer galaxy. The Milky Way band is visible to the naked eye from locations with dark skies, but it appears as a diffuse glow rather than as individual stars because the stars are too numerous and too distant to resolve individually without optical aid. The band was recognized as consisting of stars by Galileo in 1609, when his first telescopic observations resolved it into individual stars, confirming that it was not atmospheric haze or a continuous nebula but a vast aggregation of stellar points. This was the first recognition that the galaxy contains far more stars than the several thousand visible to the naked eye. From our specific position slightly above the galactic midplane, the Milky Way band appears very slightly asymmetric between the northern and southern galactic hemispheres, though this asymmetry is too subtle to perceive without careful measurement. The elevation of the solar system above the midplane by roughly 50 to 100 light-years means that the midplane of the galaxy is slightly below the equator of our view. Looking toward the galactic center in Sagittarius, all the internal structures are hidden behind the curtain of dust, making this the most featureless direction in the optical sky despite being the direction of the densest concentration of stars in the galaxy. Looking toward the galactic anticenter in Auriga and Gemini, the line of sight passes outward through progressively lower density regions of the disk and eventually into the intergalactic space, making this direction somewhat clearer of dust and populated with more nearby stars of recognizable identity. The galactic center region, while invisible optically, is the subject of intense multi-wavelength observation that has built up a detailed picture of what lies at the directional center of our galaxy. The Chandra X-ray Observatory has mapped hundreds of X-ray point sources in the galactic center region, revealing a concentration of neutron stars, black hole binaries, and white dwarf binaries in the dense stellar environment. The Large Area Telescope on the Fermi Gamma Ray Space Telescope has detected a diffuse gamma-ray emission from the galactic center region whose origin is debated, with proposed explanations including dark matter annihilation, a population of unresolved millisecond pulsars, or cosmic ray interactions with the dense gas. The Fermi bubbles, two enormous lobes of gamma-ray emission extending roughly 25,000 light-years above and below the galactic plane and discovered in 2010 using Fermi data, are among the most dramatic large-scale structures visible from our location. They originate from the direction of the galactic center and are thought to be the remnants of an energetic outburst from SGRA** or from a period of intense star formation in the galactic center region that occurred perhaps a few million years ago. Their edges are sharp in the gamma-ray and microwave bands, and they have associated X-ray and radio emission. Looking toward the galactic north or south pole in the appropriate wavelength bands, the Fermi bubbles represent one of the most striking large-scale structures in our observational view. The Magellanic Clouds, visible as bright satellite features in the southern sky, are the most prominent external galaxies visible to the naked eye and serve as reference points that the galaxy's overall gravitational environment has trapped in orbit. They are not symmetric with the north-south axis or the galactic center, but are confined to the southern hemisphere view from the solar system's position, illustrating how the distribution of even our nearest galactic companions depends on our specific galactic location. The specific direction toward the galactic anticenter, away from the galactic center and toward the outer galaxy, has historically been easier for astronomers to study than the direction toward the center because dust extinction is lower. The anticenter direction provides a view into progressively lower density, lower metallicity regions of the outer disk, and the spiral arm structure seen in this direction is part of the Perseus arm, at roughly 6,000 to 7,000 light-years, and then the outer arm beyond it. The anticenter also provides a relatively unobstructed view of the galactic halo in the disk plane, useful for studies of the halo population that cannot easily be studied toward the center where disk stars dominate the line of sight. The solar system's current galactic address is not permanent. Over geological and astronomical timescales, the solar system's position in the galaxy changes in ways that have likely influenced Earth's history and that will continue to shape the environment of the solar system in the future. Understanding the nature of this positional evolution is part of understanding where we actually live, because where we are now is a snapshot of a continuously changing situation. The orbital motion around the galactic center is the most obvious source of positional change. At 220 km per second and a galactic orbital radius of approximately 26,000 light-years, the solar system moves through roughly 1.4 billion kilometers of its orbit every day. Over 1 million years, it moves about 218 light-years along its orbital path. Over the galaxy's estimated age of roughly 13.5 billion years, the solar system has made approximately 50 to 60 orbits, though the Sun itself formed only about 4.6 billion years ago and has therefore completed roughly 20 orbits. The solar system's galactic orbit is not perfectly circular. It has a slight eccentricity, meaning the orbital radius oscillates slightly about the mean value over each orbit, ranging from perhaps 23,000 to 29,000 light-years in galactic radius over one orbital period. This variation in galactic radius means that over time the solar system passes through slightly different galactic environments, encountering different average stellar densities and slightly different distances from the major spiral arm structures. The oscillation perpendicular to the galactic plane, the bobbing motion that carries the solar system above and below the midplane with a period of about 32 to 35 million years, is geologically interesting because it correlates with the period of mass extinctions in the fossil record. The correlation, if real, suggests that the solar system's passage through the denser midplane environment periodically increases the rate of comet bombardment of the inner solar system, with comet impacts then triggering or contributing to mass extinctions. The larger-scale positional change involves the spiral arm structure itself. The solar system does not orbit at precisely the same rate as the spiral arm density pattern rotates, and so over time the solar system moves in and out of spiral arm regions. Models of the Milky Way spiral pattern suggest that the solar system passes through a major arm roughly every 100 to 150 million years, spending some time in the arm before moving back into the interarm region. These arm crossings would expose the solar system to higher rates of supernova explosions, denser gas clouds, and the gravitational perturbations of massive star clusters. The galactic coordinate system used by astronomers has the galactic center in the direction of longitude 0 degrees and the Sun at the origin, with longitude increasing counterclockwise when viewed from the galactic North Pole. This convention means that from the solar system, the galactic center is always at longitude 0 in Sagittarius, the galactic anticenter is always at longitude 180 degrees in Auriga and Gemini, and the direction of galactic rotation is toward longitude 90 degrees in Cygnus. These are fixed directions in galactic coordinates, but they correspond to constantly changing directions in the celestial coordinate system of right ascension and declination as Earth orbits the Sun and as the solar system moves through the galaxy. The precession of the galactic orbit, the slow rotation of the orbital ellipse due to the non-spherical mass distribution of the galaxy, adds another layer of positional change over very long timescales. This precession means that the point of closest approach to the galactic center, the perigalacticon, slowly rotates around the orbit, so that even the pattern of galactic radius variation over time changes over billions of years. The encounter rate of the solar system with other stars, while always very low by human standards, varies with galactic position. In the denser environments of spiral arm cores, closer stellar encounters occur more frequently, potentially sending more comets from the Oort cloud into the inner solar system on each passage through the arm. In the interarm environment the solar system currently occupies, the stellar density and therefore the encounter rate are lower. Estimates of the frequency of encounters close enough to significantly perturb the Oort cloud, within about 1 light-year, suggest roughly one such encounter per few tens of millions of years in the current environment. The visible components of the Milky Way, the disk, the bulge, the bar, the halo of stars and the gas, constitute only a minority of the total mass of the galactic system. The dominant mass component is dark matter, an invisible form of matter that interacts gravitationally but emits no electromagnetic radiation and has not been directly detected despite decades of searching. Understanding the dark matter halo is essential for understanding the Milky Way as a complete system. The evidence for the dark matter halo comes primarily from the rotation curve of the Milky Way, the relationship between the orbital velocity of stars and gas at different galactic radii and their distance from the galactic center. If all the mass of the galaxy were concentrated in the visible stars and gas, the orbital velocity should decrease with increasing radius beyond the bulge, just as the orbital velocities of the outer planets in the solar system decrease with distance from the Sun. Instead, the rotation curve of the Milky Way remains roughly flat out to the largest radii that can be measured, indicating that the total enclosed mass continues to increase with radius even where no visible matter is present. The mass distribution that produces a flat rotation curve is one that increases linearly with radius, which corresponds to a density that decreases as the inverse square of radius. A roughly spherical halo of dark matter with this density profile surrounding the visible galaxy naturally produces the observed flat rotation curve while accounting for the mass deficit between the visible matter and the dynamically inferred total mass. The total mass of the Milky Way's dark matter halo is estimated at roughly 10 to 12 times the mass of the visible stars and gas combined, or approximately 1 trillion solar masses total, with about 100 billion solar masses in visible matter and 900 billion in dark matter. The dark matter halo extends to much larger radii than the visible disk, perhaps to 300,000 to 600,000 light-years, providing the gravitational environment within which the entire visible galaxy is embedded. For the question of where we live in the Milky Way, the dark matter halo is relevant because it defines the actual extent of the galactic system. If the Milky Way is defined by its gravitational sphere of influence, then the galaxy extends to the outer boundary of the dark matter halo, which is vastly larger than the visible disk. The solar system at 26,000 light-years is not anywhere near the galaxy's outer edge in this sense. It is relatively close to the center of the total mass distribution. The density profile of the dark matter halo has been measured through a combination of observations: the rotation curve of gas and stars in the disk, the velocity dispersions of halo stars and globular clusters at large distances, and the velocities of satellite galaxies and tidal streams. The NFW profile, proposed by Julio Navarro, Carlos Frank, and Simon White in 1996 based on dark matter-only computer simulations of structure formation, provides a good description of the halo over a wide range of radii, with a density that varies as the inverse square of radius in the outer regions and more steeply in the inner regions. The shape of the dark matter halo is not perfectly spherical. Observations of the tidal stream from the Sagittarius dwarf galaxy, which wraps around the sky in a great circle, have been used to constrain the shape of the dark matter potential through which the stream orbits. Different analyses have reached different conclusions about whether the halo is prolate, elongated along one axis, oblate, flattened, or nearly spherical, with the disagreements arising from different observational data and different modeling approaches. Current best estimates suggest the halo is close to spherical in the inner regions but may be somewhat triaxial at larger radii. The dark matter halo is not smoothly distributed. Cosmological simulations predict that large dark matter halos contain numerous smaller subhalos, the remnants of the small galaxies that have been accreted and disrupted over the galaxy's history. Some of these subhalos still contain visible stellar populations, the dwarf satellite galaxies, while others may be dark, containing no stars at all because their halos were too small to hold gas against the heating of the cosmic UV background. Detecting these dark subhalos would provide an important test of the standard cold dark matter model of structure formation. The Milky Way does not exist in isolation. It is the second largest member of a gravitationally bound group of galaxies called the Local Group, which contains approximately 50 to 60 galaxies distributed through a region of space roughly 10 million light-years across. Understanding the Local Group places the Milky Way in its broader cosmological context and illuminates how our galaxy's position in the larger structure of the universe relates to our position within the galaxy itself. The Local Group is dominated by two large spiral galaxies, the Milky Way and the Andromeda Galaxy, M31. These two galaxies account for the overwhelming majority of the Local Group's stellar mass, with all other members being dwarf galaxies of various types. The Andromeda Galaxy is somewhat more massive than the Milky Way, with a stellar mass perhaps 50% larger, though the comparison depends on how the mass is estimated and the values are uncertain at the 30% level. Andromeda is at a distance of approximately 2.5 million light-years. Between the Milky Way and Andromeda, and in the outer regions of both galaxies' gravitational influence, are numerous dwarf galaxies. The Milky Way's satellites include the Large and Small Magellanic Clouds, which are the largest and most massive satellites, visible as bright cloudy patches in the southern sky and located at distances of 160,000 and 200,000 light-years respectively. Other Milky Way satellites include the Sagittarius dwarf spheroidal galaxy, which is currently being tidally disrupted and absorbed by the Milky Way, the Canis Major overdensity, and more than 30 ultra-faint dwarf galaxies discovered in recent years through digital sky surveys. The Local Group itself is part of a larger structure called the Virgo supercluster, centered on the Virgo cluster of galaxies about 50 million light-years away. The Virgo cluster's gravitational influence is pulling the Local Group toward it, contributing to the peculiar velocity of the Local Group relative to the cosmic microwave background. In the even larger context of cosmic structure, the Local Group sits near the edge of the Laniakea supercluster, the vast network of galaxy groups and clusters that forms our cosmic neighborhood at the 500 million light-year scale. The Andromeda and Milky Way galaxies are currently approaching each other at roughly 110 kilometers per second in radial velocity, with a smaller transverse component whose exact value has been measured by Hubble Space Telescope observations of Andromeda's proper motion. The two galaxies are expected to begin a gravitational interaction in roughly 4 to 5 billion years and to complete a merger over the following several billion years, eventually forming a single large elliptical galaxy. The timing of the Milky Way-Andromeda merger, currently estimated at 4 to 5 billion years in the future, has been studied using N-body simulations that model the gravitational interaction between the two galaxies' dark matter halos, stellar disks, and satellite systems. The simulations show that the merger will likely proceed through several phases: an initial close passage that creates tidal distortions in both galaxies, a period of several billion years during which the two galaxies orbit each other with decreasing separation as energy is radiated away through tidal interactions, and finally a completed merger that produces a single elliptical or lenticular galaxy. The fate of the solar system during the merger is not precisely predictable but can be statistically characterized. Simulations of the merger show that the probability of the Sun being ejected from the Milky Way entirely is small but not negligible, perhaps a few percent. The probability of being absorbed into the Andromeda Galaxy's stellar population is perhaps a few percent. The most likely outcome, occurring in the majority of merger simulations, is that the Sun remains in the merged galaxy but at a different galactic radius and in a more randomly oriented orbit than its current nearly circular disk orbit. The Sun would not be destroyed by the merger itself, because stellar collisions during galaxy mergers are extremely rare. The local group's isolation from the nearest rich galaxy cluster, the Virgo cluster at roughly 50 million light-years, determines the cosmological environment that the Milky Way and its satellites inhabit. The Virgo cluster's gravitational influence is too weak at this distance to significantly affect the internal dynamics of the local group, though it does contribute to the peculiar velocity of the group relative to the cosmic microwave background rest frame. The local group is effectively a self-contained gravitational system that will evolve through the merger of its two dominant members over the next few billion years while remaining gravitationally isolated from the broader cosmic structure. The total mass of the local group, including both galaxies and their dark matter halos plus all satellite galaxies, is estimated at roughly 3 to 5 trillion solar masses. The Milky Way's share of this is approximately 1 trillion solar masses, predominantly in its dark matter halo, with the visible baryonic mass being a minority. The local group is embedded in a volume of space where the mass density is slightly above the cosmic average, enough to keep the group gravitationally bound against the general expansion of the universe, but not enough to prevent the local group's environment from participating in the Hubble flow at larger scales. The specific galactic address of the solar system, the properties of the location it occupies, and the timing of its formation within galactic history combine to tell us something important about the conditions that made Earth's biological history possible. Whether this information implies anything profound about the relationship between location and life is worth examining carefully. The galactic habitable zone argument proposes that the solar system's position at intermediate galactic radius is not coincidental but is a necessary condition for the kind of stable, long-duration planetary habitability that allowed complex life to develop over 4 billion years. The inner boundary of the habitable zone excludes regions where radiation, gravitational disruption, and supernova frequency are too high. The outer boundary excludes regions where metallicity is too low to form Earth-like rocky planets. The solar system sits within the proposed habitable annulus. The timing of solar system formation, roughly 4.6 billion years ago in a galaxy that had already been forming stars for roughly 9 billion years, also appears relevant. By the time the solar system formed, multiple generations of stellar nucleosynthesis had enriched the interstellar medium to the metallicity required for forming Earth-like planets. The oxygen, carbon, nitrogen, silicon, iron, and other elements that constitute Earth and its biosphere had been produced in previous generations of stars and distributed through the interstellar medium before the solar nebula condensed from it. The specific position within the Orion Arm, in the interarm region between the Sagittarius and Perseus arms, may have provided an environment that is calmer and more stable over geological time than an arm core position would have been. The relatively lower rate of nearby supernova explosions may have allowed life on Earth to develop without the frequent, potentially sterilizing radiation events that would be more common in a higher density environment. Whether these galactic scale factors are truly necessary conditions for life, or whether life could develop in environments with substantially different galactic addresses, is genuinely unknown. The sample size of a single inhabited planet around a single star in a single galaxy, makes any statistical argument about galactic habitability conditions extremely speculative. What can be said with confidence is that the solar system's galactic location is not extreme or unusual in ways that would obviously preclude habitability, and that several of its properties fall within ranges that theoretical arguments suggest are favorable. The specific metallicity of the solar neighborhood, the abundance of heavy elements in the interstellar medium from which the solar system formed 4.6 billion years ago, is another measurable consequence of our galactic location. The solar system's metallicity is slightly higher than the current average for disk stars at the same galactic radius, an anomaly that may reflect formation in a region that had been locally enriched by nearby supernovae shortly before the solar nebula condensed. This slightly elevated metallicity contributed to the formation of a rocky planet with a mass close to Earth's and a chemical composition rich in the elements required for plate tectonics, the carbon-water-silicate cycle, and the eventual development of life. The question of whether our galactic location is a meaningful selection effect for the development of complex life, or whether complex life could equally well arise anywhere in the galaxy given sufficient time, is one that cannot be definitively answered from a sample of one. The anthropic argument is unavoidable. We necessarily find ourselves in a location compatible with our existence, which does not tell us whether other locations would also be compatible. But the consistency between the proposed galactic habitable zone and our actual location, combined with the specific properties of the solar system that appear to result from its galactic location, suggests that galactic environment is at minimum a relevant factor in planetary habitability even if it is not the determining factor. The continued discovery of exoplanets throughout the galaxy, including rocky planets in the habitable zones of stars at various galactic radii, will eventually provide an empirical test of whether location-specific factors actually influence the frequency of life-hosting planets. If rocky planets in the inner galaxy or the outer disk prove to be systematically less hospitable to complex life than those in the proposed habitable zone, the galactic location hypothesis would gain empirical support. The galactic address of the solar system, assembled from centuries of progressively more sophisticated observation and refined by the extraordinary precision of the Gaia mission and complementary surveys, tells a story that is both more specific and more interesting than the vague sense that we are somewhere in the Milky Way. We are 26,000 light-years from the galactic center, in a minor arm or spur between the major Sagittarius and Perseus arms, embedded in a cavity of hot, low-density gas called the local bubble, at a height of about 50 to 100 light-years above the midplane of the thin disk, traveling at 220 kilometers per second around a galactic center dominated by a 4 million solar mass black hole, completing one orbit every 225 to 250 million years while bobbing gently above and below the midplane on a 32 to 35 million year timescale. This address is a physically real, precisely measured, scientifically grounded description of a location in the cosmos. What makes this address more than a list of coordinates is what it implies about the environment the solar system inhabits and the history of that environment. The interarm position in the galactic habitable zone appears, on the available evidence, to have been a favorable address for the development of long-duration planetary habitability. The local bubble provides an unusual local environment. The specific timing of solar system formation at intermediate galactic history gave access to the heavy elements required for rocky planet formation without the extreme conditions of the very early or very late galaxy. There is also something philosophically significant in the process by which this address was established. Determining where we are in the Milky Way required overcoming the fundamental limitation of our embedded perspective, the fact that we cannot step outside the galaxy and observe it directly. The history of this determination is a story of human ingenuity in the face of this limitation. Using globular clusters as reference points when stars were too obscure to count, using radio waves to penetrate the dust when optical observations were impossible, using the precise motions of stars as revealed by Gaia to reconstruct the three-dimensional structure of the disk from within it. The address we now have is better calibrated than any previous version, but it is not final. Every new survey, every new instrument, every new method of probing the galactic structure from our embedded position refines some aspect of the picture. The Milky Way's spiral arm structure at large scales remains less well characterized than the nearby arm environment. The exact extent and mass of the dark matter halo is uncertain. The history of the local interstellar environment over the past billion years can be reconstructed only in outline. What we know precisely is that we live in a specific, identifiable, well-characterized location within a barred spiral galaxy of intermediate mass, at a specific radius from the center, in a specific structural feature of the disk, in a specific local environment. We know this location's history well enough to assess its relevance to the development of life on Earth. And we know it well enough to recognize that this location, while perhaps favorable for life in several ways, is not cosmically special. It is one address among the 200 to 400 billion stellar addresses in this single galaxy, and among the trillions of galaxies in the observable universe. This absence of cosmic specialness is not diminishing. It is the actual content of the Copernican principle, the recognition that our location is not physically privileged, that the laws of physics are the same everywhere, and that the universe is arranged to allow the development of complexity in many places and not to concentrate it exclusively in our neighborhood. We happen to live here, in this particular corner of this particular galaxy. The universe is vast enough that this is not the only place it has happened. The address itself tells us something about how science works. The determination of where we live in the Milky Way was not accomplished by a single observation or a single insight. It was assembled piece by piece over centuries, with each piece requiring overcoming a specific technical or conceptual obstacle. Shapley's globular cluster work required the development of Cepheid distance techniques. The discovery of dust absorption required the calibration of how reddening and extinction vary with distance along different sightlines. The radio mapping of spiral arms required the invention of radio astronomy and the theory of the 21-centimeter hydrogen emission line. The infrared mapping of the central bar required the launch of sensitive space infrared telescopes. The Gaia parallax map required decades of development of space astrometry, precision optics, and the computing infrastructure to process 1 billion measurements simultaneously. Each of these technical achievements was driven not by a single problem but by a broad program of astronomical research, of which the question of where we live in the galaxy was one of many motivations. The answer to where we live therefore represents an accretion of human knowledge across a broad front, not a targeted solution to a single defined question. This is characteristic of how scientific knowledge about the natural world tends to develop. Not through the direct pursuit of interesting questions but through the slow accumulation of capabilities that eventually make those questions answerable. The galactic address of the solar system is, in the deepest sense, the outcome of the universe's history played out over 13.8 billion years. The formation of the Milky Way from primordial gas, the buildup of the galactic disk through star formation and chemical enrichment, the development of the spiral arm structure and the galactic bar, the sequential supernova explosions that created the local bubble, the formation of the solar system in the interarm region at intermediate galactic radius from material enriched by earlier stellar generations. All of these events conspire to produce a solar system at this specific address at this specific time. That we are here to note the address is itself part of the story.